Today we'll be looking at lesson 303, Function Junction. Our objective today is I can write the key features of a function in any representation, a table, a graph, an equation, or a story, in 2 out of 2 problems. So this is what we've been looking at already in this unit. We've been doing key features of functions. And now we're just going to keep practicing with different representations. We're going to start off with a thought experiment a little bit. We're going to look at a few different graphs and decide which one is different. We're going to look at the following graphs, choose one that is different from the others, and I'd like you to consider key features that we've been talking about, things like domain, range, maximum, minimum, whether it's continuous, discrete, discontinuous, whether it's a function at all. And it looks like this got a little bit cut off, but there are many correct answers here. So if you come up with something that I don't come up with, that doesn't necessarily mean it's incorrect. It could be a thing that I didn't see. So there are lots of different answers here. So I wanted you to take a look at these graphs. Maybe pause the video for a minute and try to find one graph that you think is unique in some way. It has a feature that none of the other 4 graphs have. So pause the video, see if you can find one. So each of these graphs has at least one unique feature. If we look at A here, A has an absolute minimum. So if we look at the other graphs, we would assume that these are probably going down here, this one's going down, and then this one would probably continue like this if we assumed that one was continuing. So A is the only one that has an absolute minimum, has a minimum that we could put a number on. Now let's look at B. You may have noticed on B that it has an open dot. It's the only one that has an open dot. That is an unincluded endpoint. Or also that it jumps here. It jumps from this open dot to this closed dot, which makes this a discontinuous graph. That's what we mean by discontinuous. It means otherwise it's continuous, but there is a jump in it, or several jumps between the continuous parts. So this is a discontinuous graph and the only one with an open endpoint. You also may have noticed this is the only graph that is always increasing. You'll notice here this one is decreasing, then increasing. This one kind of has different sections. This one's increasing, this one's decreasing. This one is always decreasing, and this one is increasing and then decreasing. So B is the only graph that is always increasing. C is the only graph that is not a function. If we do the vertical line test, you'll see it passes through twice. So C is the only one that is not a function. D has a few things that are unique about it. One is that it's a discrete. We see they're listed as dots, or they're drawn on as dots rather than continuous lines. So this is the only one that's discrete. Or you might have thought of that as dots. This one also is decreasing the whole time. It's the only graph that's decreasing, always decreasing. And then on E, this inverted parabola going down, this one has an absolute maximum. And it's the only graph that has that. Absolute maximum. You see this one's going up, so there is no absolute maximum. This one is also going up. This one is going up. It'll go up forever. This one is going down forever, but on this side it would go up. So this is the only graph that has an absolute maximum. So good job, whatever you found there. If you found something I didn't find, that's cool too. These are all just unique features of these graphs. It distinguishes them from the other graphs. So now we're going to take a look at functions. We're going to talk about some key features of functions in different representations. We're going to use the appropriate math notation on each of them. We'll see what that means. Okay, this table represents a discrete function defined on the interval from 1 to 5. Oh, we have a few. It's actually a really dense sentence with information. One thing it tells us is it's discrete. So we have to remember what discrete means. It means dots that are not connected. So that tells us, would we have a value in here, like a value at 1.5? Would that exist? The answer is no, it would not exist, because this is only the dots. So the numbers in between the dots don't exist. The entire function is defined here as these dots. This also tells us, the sentence tells us that it's defined on the interval from 1 to 5, so the values from 1 to 5, inclusive, because it's square brackets. We have a value at 1, we have a value at 5, but we don't have any values outside of there. The only values we have are the ones from 0 to 5. So let's look at our domain. What are our valid input values here? What's our valid inputs? Remember, our inputs are over here, our outputs are over here. What's our valid inputs? Well, we know it's 1 to 5, so we have a couple of ways that we could think about writing this. One of them is not the way we want to do it, though. So let's look. One way we could do it is we could just list them out, 1, 2, 3, 4, 5. And when we list them, when we have a set, we use curly brackets. And then another way we've talked about it is interval notation, where we start with our lower bound, comma, upper bound, and then we use square brackets here because those are included endpoints. Now, one of these ways is an accurate representation of this function, and one is not. Let's talk about why. This interval notation indicates all the values in between 1 and 5. So it would include 1.5, 2.5, 3.67921, all of those numbers in between 1 and 5. But we said, because this is discrete, 1.5 is not in this domain. 2.5 is not in the domain. 3 point whatever, 6719268, not in the domain. So since this is not continuous, we will not write it in interval notation. We need to write it as a set. We list the set elements out because they are discrete. So we could generalize that and say discrete, we write as a set in curly brackets, and continuous, we write as an interval. And that could be square brackets or round brackets, or one of each. Okay, so this one is discrete. We're going to keep writing our curly brackets. What is our range here? Remember, there's no values in between, so we would just list our outputs out. What is our range? It's our valid y values, so this will be 5, 10, 40, 80, and 160. That's our range. And once we have our range, our minimum and maximum are pretty easy. We can just look at the smallest value and the largest value. Notice that we wrote these in order, and that makes it extra easy to find the minimum. We just find the smallest one. The first one in our range is a 5. That's our minimum. That is our smallest output value. Our maximum is 160, our largest output value. Intercepts in a table we haven't talked about much. We've looked at them on our graph a little bit. But what we're looking for when we look for intercepts in a table is we're going to look for zeros, anywhere we can find zeros, and not just in numbers, not like in 10 there, but a zero on its own, a fully zero input or zero output. Do we see any of those in this table? A zero input or a zero output? There aren't any. So there are no intercepts on this function. Let's look at intervals of increase and decrease. So where is this function going up? Let's see, we're adding, we add 5 there, we add 30 there, we add 40, we add 80. So the rate of change is changing. It doesn't have a constant rate of change. But it is always going up. We're always adding, right? We're getting bigger numbers. Adding, 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 adding. We add the whole time. So the interval of increase is the entire function. This function is defined from 1 to 5. We could also write the interval of increase that way, 1 to 5, including the bounds because we have points there. Now, if the whole function is increasing, that means there is no interval of decrease, right? There's no place on this function where we're going down. Let's look at the next problem. So now we have a graph. This graph is kind of curvy. It has a distinct endpoint here and a distinct endpoint here. Pause the video and see if you can write down these different key features, and then we'll talk about what they are. So the domain is our valid input values. It's from here to here, right? So we start here. And this is the beginning of our valid inputs. And it's continuous all the way over to here. And this is the end of our valid inputs. So it goes from, looks like -6, -7, to -8. It's -8 right there, to a +10. Now remember, we had 2 ways to write this. We could have written it -8, -7, -6, -5, and on up to 10. Or we could write this as an interval. One of these ways is correct, and one of these ways is not appropriate for this particular function. And the key, again, was to ask, is it valid? Is there a point here at 1.5? Is 1.5 a valid part of our domain? Well, sure. Yeah, there's a point right there. How about at 3.7? Is that a valid part of our domain? Yeah. Yeah, this is a continuous function, so every number in between these two is valid. So this set notation doesn't have those decimals, so that is not the one we want to use here. We want to use the interval notation that includes all the numbers in between -8 and 10. Now once again, when we do range, this is continuous, so we're going to be using an interval again. Our valid y values, this is our bottom y value, our lowest one. It's going to start there. Do a circle there, an open circle. And then our top value, looks like there's a peak there, but this dot is a little bit higher, so this is our maximum value. I'll bring it all the way over and see where it hits. It looks like it hits at 5. So if we go down 1, 2, 3, this is a -3. So our range is going to be from -3 to +5. Remember, we don't write at 5 to -3 because that would be in decreasing order. That would be out of order. We need to write it with the lower bound first. So the lower bound is -3, upper bound is 5, and both of those dots are included. They're filled in, so we do square brackets. Now once we have the range written down, it makes the minimum and maximum easier. The minimum is just the lower bound of the range. the maximum is the upper bound of the range. How about intercepts? Can you see where this graph is crossing an axis? Maybe it crosses an axis more than once, or it crosses two different axes. Yeah, there are a couple of places. There's a y-intercept right there, and there's an x-intercept right here. So our x-intercept is at, looks like -5, -6, maybe about -6.4, about that, -6.4. That's where it crosses the x-axis. And then the y-intercept is going to be where it crosses the y-axis. Where would that be? Let's see, up here. That's at 1, 2, 3, 4, and just a little bit, maybe 4.2. Let's call it that. All right, so how about intervals of increase and decrease? Where is this function going up? Well, it looks like it starts going up, and then it goes down again, and then it goes up again at the end. Looks like it might hit its peak right about there. It might hit a value right about there. So where is it increasing? Well, it starts at -8. We start at -8 and we go all the way up to about -0.5. So that's going to be one interval of increase from -8 to -0.5. Then we have an interval of decrease where we're going down. That's going to be from about -0.5 to, looks like 7. And then we have another interval of increase, a place where the function is going up. So this starts at about 7 and goes up to, looks like 10, 7 to 10. So that's going to be another interval of increase. So we have two intervals of increase on this graph and then one interval of decrease. And our last question here is this a function, yes or no? Well, we can draw vertical lines. Looks like anywhere we draw a vertical line, it will only go through once. So that makes it a function. Yes, this is a function. All right, moving on to the next one. Oh, we have a story here. So Marcus bought a $900 couch on a 6-month loan. He pays $50 each week. Describe the key features of the relationship between the number of weeks and the amount still owed on the loan. So what might we use to help us look at this? We have some tools to help us model stories. We could use a table. We could use a graph. How about we try using a graph? So we know that this is all going to be positive values, right? He owes $900, then that's going to go down, and then the number of weeks is a positive value as well. So I'm just going to do this one quadrant. This will be our y-axis, this will be our x-axis. And maybe up here we have 900, 3, 4, 5, 6, 7, 8. Oh, I didn't quite get 9 in there, did I? Okay, there you go, 9. Not very evenly spaced out, but it's fine. 1, 2, 3, 4, 5, 6, 7, 8, 900. So this one's 500. We have 200 here. And then we're going to go out a number of weeks. So 1 week, 2 weeks, 3 weeks, 4 weeks, and so on. All right, let me grab a different color really quick so we can see our marks, maybe blue. So we're going to start this loan at $900. We know at week 0, Marcus owes $900 on this couch. And then at week 1, he has paid $50, so it goes down to $850. So at week 1, it's going to be right about there at $850. This one's 900. At week 2, it'll go down to 800. Week 3 down to 850. Week 4, 750. Week 4 at 700. And if I'd drawn these lines evenly spaced out, this would look like a straight line. And the question is, it's going to go down, eventually he's going to have this loan paid off, right? Eventually it's going to hit 0. Where does it hit 0? How do we figure that out? Well, he owes $900, and he's going to pay $50 per week. So if we multiply that by 1 week over $50, the dollars cancel, and I do 900 divided by 50, we get 18 weeks is the units we have left, so 18 weeks. So this will be 18 up here. So at 18 weeks, we hit 0. At 17, it would be 50. At 16, it would be 100, and would go up to that line up there. So now we have kind of a graph. We know that these dots would continue in between. We have to ask ourselves, would we connect these dots? Well, no, because we're going to pay $50 in chunks, right? So each of these dots represents a payment, and there's no payments in between. So we don't connect the dots. This is a discrete function. Since this is a discrete function, that tells us the domain is going to be a set. And it's our valid input value. So we start with 0. There's a value at 0, at 1, at 2, at 3, at 4, all the way up to 18. So we can go 0, 1, 2, 3, all the way up to 18. Or if you wanted to say this is integers between 0 and 18, that's another way to write it. Either of those would be fine. Remember, we're not going to write it like this. We're not going to write it like that because we don't include 0.5, 1.5, 2.7, 3.92438. We don't include any of those numbers because the dots only exist at the integers. Okay, so our range should be similarly in curly braces. What is our valid output values here? We said it's 900, 850, 800, 750, and so on, all the way down to 0. So we could write it that way, 900, 850, 800, and so on. But there's actually a convention in mathematics when we write a set that we're going to write it in order. So we're actually going to start at 0 and go up instead. We're going to write the same numbers, we're just going to write them in increasing order instead of decreasing order. So 0, 50, 100, 150, 200, all the way up to 900. That's our valid range on this function, only where the dots exist. Now that we have the range written, the minimum and maximum are a bit easier. The minimum is going to be the smallest value, 0. The maximum is going to be the largest, which is 900. Then we can look at our intercepts. Where does this cross the y-axis, and where does it cross the x-axis? Here's the y, here's the x. So we do have both an x-intercept and a y-intercept. The x-intercept is where it crosses the x, here at 18. The y-intercept is where it crosses the y, and it's up here at 900. Now we're looking for the interval of increase. Where is this function going up? Well, let's see, it's going down pretty much the whole time, so there is no interval of increase. That happens sometimes. There isn't one. And this slide got a little bit skewed. We're supposed to be looking for the interval of decrease as well, but it got pushed off the page. Where was the interval of decrease? We said the interval of decrease is the whole function. Or since it's defined on 0 to 18, we could also say the interval of decrease is from 0 to 18. So those are the key features of this function from a story. All right, we've got one more here. Graph the function, then determine the key features. Pause the video, see if you can do this one on your own, and then we'll work it out. Okay, so I'm going to draw some axes on here. There's our x-axis. Oh, that's not a very straight line. Let me see if I can grab a straight line. There's our y-axis. So here's our y, here's our x, and we're going to graph mx plus b. This is in slope-intercept form. Our slope is -2, our y-intercept is 4. So we go up to 4, 1, 2, 3, 4. We put a dot there. We do our slope, which is -2 over 1. So down 2, 1, 2, right 1. And then we draw a line in between them. Right about there. Well, close. Let's see if we can get this line right on those dots, maybe. Very close. There we go. That's much better. Now, we could draw this line out further, but notice that it says x is greater than or equal to 0. So actually, that's not a valid domain. This is not a valid domain where x is less than 0. So I'm going to undo what we just did there. This is our valid function, only where it's going down over here. It is going to go down forever, but it starts at this point here. So what is our domain? Our domain is our valid inputs. It starts at 0, and it looks like it goes forever to the positive side. It never stops, so our endpoint is actually going to be infinity. We write infinity like this. It's a little infinity symbol. So our domain is going to start at 0 and go up until infinity. And there's a convention in math. When we have infinity, we always use a round bracket. We use a round bracket because we can't include infinity. Infinity goes on forever, so it isn't actually a number. It's more like a concept. It goes on forever. Since you can't include a non-number, we use a round bracket. Okay, so what is our range? We're looking at our valid y values now. This is our maximum. You can see that's the top. This is at 1, 2, 3, 4, looks like. So 4 is our maximum, and now we go down. This is what we're going to call negative infinity down here. It goes down to negative infinity. This is positive infinity on the positive x-axis. But since this is the y-axis, we're going to negative infinity. Now, we might be inclined to say, okay, it starts at 4 and goes to negative infinity, and write it that way. -4, comma, negative infinity. But we need to remember this is the lower bound. This needs to be the lower bound, and this needs to be the upper bound. That's the way we always write intervals. But this is upper, right? This is our maximum. This is our top value. So we actually wrote that backwards. This is not how we will actually start with negative infinity and go up to positive 4. Oh, there shouldn't have been a negative here in the first place. We'll go up to positive 4 and include it. So that's how we'll write the range. Negative infinity with a round bracket, it's not included, and it goes up to the value 4. It's very common to write those in reverse order, but that's an accident. It should actually be written with the lower bound first. So now what is our minimum? Well, our minimum is pretty easy to spot once we've written the range correctly. The minimum is just the lower bound, negative infinity. Our maximum is going to be 4. How about intercepts? Do you see anywhere this crosses the x or y axis? Crosses the x there, crosses the y there. So our x-intercept is going to be 1, 2, and our y-intercept is going to be 4. Now let's look at intervals of increase and decrease. Do you see anywhere on this function it is increasing? Nope, it's not going up anywhere. There's no interval of increase here. And then the interval of decrease is going to be the whole function. Or we could also write that as 0 to infinity. So it's increasing from here forever this direction. So that wraps up our practice today. I can write the key features of a function in any representation, a table, a graph, an equation, or a story, in 2 out of 2 problems.